Okay, so in this video we're going to be doing another example on Navier-Stokes. Alright, so Navier-Stokes is a differential equation that expresses conservation of mass and momentum for fluid. And if we solve this equation, we're able to get a function that describes the velocity and sometimes pressure distribution within a fluid. Okay, so here's a little bit more of a complex example than the previous one. Here we have vertical flow between parallel plates, and the plates are both going to be stationary, right? And so there's going to be a vertical pressure gradient that drives the flow upwards, but gravity is also going to be pushing the flow downwards, right? And so think of this as like a pipe that routes water from the ground up to like a higher story building, okay? And just like we normally do in Navier-Stokes problems, we want to compute the velocity profile between the two plates. Okay, so just like normal, we're going to start with our assumptions. So here is the full momentum Navier-Stokes equations. This is in the y direction because we're in vertical flow. And these are all the terms that we're going to cross out due to our assumptions. Okay, so most of these assumptions are fairly standard. The only thing is that because we have the pressure gradient and gravity, we're going to leave that within the equations. Here. Okay, and so we end up with a formula that looks like this, and this is the one we're going to be solving for by direct integration. Okay? So before we do that, let's go ahead and state our boundary conditions. And so our boundary conditions are both going to be no-slip boundary conditions. And so they're going to be at stationary walls. And so at both the left wall and the right wall, we're going to have a zero velocity. Okay, so let's get to work on integrating. And so here is our differential equation. I've went ahead and divided by the kinematic viscosity so that we have kind of a clean left-hand side. And after we apply the first integration, everything on that right-hand side there, the pressure gradient term and the gravity, those are all essentially constant. And so we're going to treat it all as just kind of one constant. And so when we integrate, we kind of group them together with the parentheses, and we end up with just a linear term x. Okay, and of course, since we're doing an indefinite integral, then we have to add an arbitrary constant c1 as well. Okay, so let's go ahead and do this one more time. So let's go ahead and integrate this out. And on the left-hand side, we get v of x, and on the right-hand side, we get the integral of x, which is 1/2 x squared, times the pressure gradient and the gravity term. Then we have c1x plus c2. And at this point, we're ready to apply boundary conditions. Okay, so there is our general solution. So let's go ahead and start applying boundary conditions. So the first one here is going to be a no-slip boundary condition on the left wall. And the left wall is defined at x is equal to minus L over 2. Okay, and so we plug that in, we get that expression. And then when we apply the condition on the right wall, we get a very similar formula here, except for the C1 term being the opposite sign. Okay. And so this is a little bit different than before because, from each of these equations individually, they both still have C1 and C2. And so we can't solve for one kind of outright. But what we notice here is that, these two equations are very similar to each other, but the C1 terms have the same magnitude but opposite signs. And so what this is going to allow us to do is it's going to allow us to add these two equations together. And so we're basically just going to stack them one on top of each other and then add them together. And then what we'll see is that C1 term is going to cancel out. Okay, and so by performing that addition, then we get 1/4 times the pressure gradient term minus gravity L squared plus 2C2. Okay, and so this equation is great for us because it's eliminated C1, and we can solve it outright for C2. Okay, and so what we get is C2 is equal to minus 1 over 8 times 1 over mu dp dy minus g over nu L squared. Okay. And so now that we have one of the constants, we can just go ahead and plug it in, back to either of the boundary conditions, solve for C1. Okay, so let's go ahead and do that. And so we plug in for C2. And actually what we see here is that, both the first term and the purple term here are exactly the same, but opposite signs. And so they're going to cancel out. And so that's going to give us C1 is equal to 0. Okay. All right, so let's go ahead and put it all together. And so now that we solve for C1, C2, we can go ahead and plug that back into our general solution. And what we get is that the velocity distribution, v of x, is equal to 1/2 times 1 over mu dp dy minus g over nu times x squared minus L squared over 4. Okay. So this is an example that you can see what to do with the pressure gradient term as well with gravity, as well as a little bit more complicated boundary condition assignment. Okay. And what you'll notice here is that whenever you have the pressure gradient and gravity, our solution takes the form of a quadratic function. Okay, and so that's something that's key, something that's really important to remember with Navier-Stokes, that whenever you have some kind of internal forcing, whether it be pressure gradients or gravity, you should get a quadratic form in the solution.